Good evening, folks. It's me again, and it's Friday night. I just came back from seeing you guys at discussion and lecture. So I know that you guys want more of me and more of, especially you want some radicals because I've been talking so much about them. And so, you want radicals, and all I can say is, poof, you have two more wishes. So there you go. So here I am, and we're doing this. I'm kicked off my tie, and we are gonna talk about some radicals for a little bit, and then it won't be too long, just a little bit, just to get us started, because I want to have two full classes next week, and then the Friday I want to have a review for the final. With some interesting information on there as well too. So I just rather just do this real quick. It won't be too bad. Just follow along, and I just opened up a fresh bottle of coffee. So we'll just gonna have some coffee, and gonna have a little sip. Oh God, that's good, right? Let's just do this, right? Let's just talk about some radicals. All right, here we go. So free radicals form when bonds break homolytically, using homolytic cleavage. Okay, so what does that mean? So most of the stuff that we've talked about before is a heterolytic cleavage of bonds, right? Where the entire pair of electrons goes to one partner. So if X is carbon, for example, and Y is subbromine, for example, and you're doing a heterolytic cleavage, right? What happens here? This whole pair of electrons here just swings on out to that bromine, I think we're calling it, and that pair of electrons just resides there. All right, and this carbocation, exists as per this, right? So just the entire pair of electrons just goes. All right, but there's, the entire thing goes. But with homolytic cleavage, one half of the bond breaks, and one electron goes to one species, the other electron goes to the other one. Okay, and that's not too far out to be able to consider. There is a weird little convention though that we use for our stuff, that when we talk about like electron pushing and mechanisms, we normally use the double barbed arrow here, which is just traditional arrow here. I gotta change pen color. This is just way too light. Let me get a better color. Here. Blue. Let's try blue. Yeah, blue works out better. All right. So we use this double barbed arrow here, right? And so it's that. But for radicals, we use a single barbed arrow, and that's a bad arrow. It's not pointy. Ink. Oh, that's even better. Okay, good. See? All right. So there's your arrow. We just make sort of a half arrow, and the reason why is because, well, if we're having a pair of electrons move with a full arrow, then hey, we're so clever. We'll just move one electron with a half arrow. See how clever we are? Oh, we just can't get over ourselves. All right, so that's the convention about why to use the single barbed arrow versus the double barbed arrow. All right, and let's talk a little bit about the character of these radicals. Okay, so carbocations, for example, has an empty p orbital. Is an sp2 hybridized, species. It is trigonal planar, as per what you'd imagine for an sp2 hybridized thing. A carbocation has a plus charge there, and your p orbital is available. There's no electrons in it. Now that's sp2. sp3 is for something like a carbanion, where you have where you have a carbon where you have a pair of electrons on it, and there's nothing else on this to share that pair of electrons. That's why it's a carbanion, right? Because this is a pair of electrons, it has a minus charge, and that's an anion. And since it's on a carbon, so it's a carbon anion or a carbanion. All right, sort of a portmanteau of those two words. A portmanteau is a word for when you smush two words together to make a third word. Okay, so a carbanion. All right. And this is an sp3 hybridized. This is a trigonal pyramidal thing, as you might imagine. All right. All right. So where does radicals fit into this? So radicals fit into, well, it's weird you say it, because a radical is sort of in between. If you look at it, it's one electron. It's in the p orbital. All right. So it's in between a carbocation looking thing. Where it has, some electron density like a carbanion, but not as much. So it looks like maybe like a carbocation, and that's sort of where it does share. It's sort of similar between these two species over here. This guy here actually exists above and below the plane, like all this other stuff does, right? Less so like this. This exists in one position essentially, But this travels between the top lobe and then the bottom lobe, right? So you do see there is some shaping here, right? There's like a sort of a trigonal, like a shallow trigonal pyramid here and here, right? You see that? But they interconvert so fast, right, that they sort of average out into this planarity here. So for all intents and purposes and for all argument's sake, we still say that even though you have some electron density here in some of these lobes, it is still going to be a trigonal planar, because this trigonal planar here is sort of an average of these two rapidly interconverting trigonal pyramids. All right, so even though we see this and this and this and this, right, we still say it's trigonal planar, and we still sort of all agree it's going to be an sp2 hybrid species here. Okay, this is a singly occupied molecular orbital, and this can interact with orbitals that are both occupied and unoccupied. Okay, just so you know that. All right. Let's talk about free radicals and stability. Okay, so your book talks about stability, and it's a good thing to talk about. But let's talk more about things that are more reasonable to talk about, right? Like, let's not say stability. Let's just say reactive or reactivity. All right. So unstable refers to something that's that could be that's maybe a bad thing. It's not a stable compound. Well, that could be the case, but let's talk about it from the positive perspective. Let's talk about it in terms of being reactive, like you want it to react with a compound, and that's good. You want it to do that, all right? And so let's say it's reactive, okay? And so that's what we're going to say from here, okay? So look at this. So if you have a methyl here, and you have so you have a methyl primary, secondary, tertiary. I think you see sort of where we're going here, right? We're going to do a comparison between like this essentially and carbocations, carbanions, and everything else, right? Look at this. So this bond here is 493. This bond here is 423, and it goes down. Okay. So this decreases the bond dissociation energy from methyl to tertiary. All right. But as you decrease the bond dissociation energy, from here to here, the bond gets easier to break or to cleave. Right. Go from here to here, you increase the radical stability. All right. So from here to here, if you form a radical between, if you form a tertiary radical versus a methyl radical, a tertiary radical is going to be a lot more stable. One of the things that you might have evidence for that is that it is, this bond here is much more easily broken, so it's more willing to break this bond to afford you the radical. So that's one way to look at it. All right. That's just one way to look at it, okay? And we'll go into this in a minute, a little more into this in a minute. But before I continue, check your errata. The values in your book, I believe, are incorrect, and the errata, I believe, has the correct values. Check both errata, both for your textbook and your answer key. Your answer key might also be a little bit off, so just check that real quick, okay? All right. So for homework, just for funsies, okay? We're gonna look at radicals and compare those to carbocations and carbanions, and compare the stability versus the reactivity, all right? And draw the MO diagrams of each. So tell me where some of the electron density is, right? Like, and you can do this, using like the allylic radical, and then maybe the allylic carbocation and the allylic carbanion. Those are three easy things to be able to compare. All right. So let's go. Let's see this. All right. So decreasing bond dissociation energy, methyl primary, secondary, tertiary. Okay. And so this goes from here to here, and this is the most easily formed radical, right? And then you can go even further down, right? Look at this. So here's tertiary from here to here. And look, allylic and benzylic, okay? And so what's a bigger factor here? Hyperconjugation or resonance here? Well, it's funny because we can talk about hyperconjugation up to the point of here to here essentially, right? But when it comes to this, I mean, hyperconjugation is important, but this has lots of a lot of potential resonance that can help it stabilize, right? So that's a very important thing. So here, when we're talking about a certain continuum, we have to know it's part of our continuum. Part of it will be something that maybe won't have resonance, and some that will have resonance. But when it comes to resonance sort of wins out over hyperconjugation. Okay, so that's sort of how that works. All right. And so, so why does that happen? Why does why is hyperconjugation so important though in this guy here? Remember what hyperconjugation is, right? Remember if we have here's our carbon dot, and here is our, and I'll just draw one side out here so we won't have to spend too much time on this. CH3, CH3, C, and then we'll draw these H's out like this. All right. All right, there's that. Okay, so here's some radical density. So here's some electron density here, right? Why is this so stable? Well, remember, it's a radical, so it's not as reactive as some other things, but it's pretty reactive. But overall, it still would love to have some more electron density. It wants to have some. It wants to be paired up with something. That's how overall the stability works with this. It wants to be paired up, right? So how can it get some electron density? Just through hyperconjugation, like you might imagine. And if you take any of these carbon-hydrogen bonds that are very polarizable, you know what I'm darkening in here right now is sort of the carbon-hydrogen bond, right? That is polarized. So here, towards the hydrogen, you have less electron density on this side, which is sort of why this is so pointy here. And this carbon here just sort of sucking all the electron density towards it as the carbon is more electronegative, right? So this has more electron density here on this side of the bond than this side of the bond. Why? Carbon's more electronegative. That's sort of the hyperconjugation theory, right? Just sort of why this no, that's not hyperconjugation. This is why this is so polarizable. Carbon is more electronegative than hydrogen is here. Where hyperconjugation comes into is that when you have all of these things sort of feeding down some electron density into the species here. I'm drawing remarkably well for all the coffee I drank. Let's just say that. You know, just like this buildup of electron density around that carbon, and if you have all that electron density, this electron here, like sort of feels that, and this feels the electron density here. So this sort of also funnels down into this as well. So you have some electron density funneling down into this as well. All right. And so this guy here is trying to support this lone electron right there, okay? And so that's how, just like as if this was a carbocation, this also wants to support that less than full pair of electron system there, right? So hyperconjugation, stabilizes this, this radical like it would stabilize a carbocation. All right, so that's all you have to know about that. All right, it's again the same old hyperconjugation sort of argument that we made from before. Okay, all right. So let's draw some resonance. All right, draw all the canonical resonance forms of the allyl radical. No problem. All right. This is the allyl radical, not Ali Sheedy, which I'm also prone to draw, but not right now. We'll save that all for my other internet job. All right. So here's your. Ooh. Okay, that's a little crazy. All right, there's that. There's your allylic carbocation. Now we want to do the radical, but let's just draw the carbocation real quick, okay? So here's how that goes. So here's a I'll just draw carbo. Why am I doing Dory from Nemo? Cation. Carbocation. If you can, okay, that's carbo, not carbo. Carbocation. All right. So there's that. If you have, and here you would obviously recognize this guy here has resonance, right? So you have a pair of electrons here. You want to move it from there to there. You take your one double barbed arrow, and there you go, right? Here's your double-headed arrow to show some resonance. And then there's that, and there's that, and there is this, and we're all happy, right? So there's your carbocation, right? But now let's draw the allylic radical and see how this is a little bit different than that, okay? All right, it's a little bit different than that. All right, you know what? Let me just clear this out. Okay, so you have this. You can pause it and write this down, but I'll probably be recopying this down here anyway. All right, let me just clear this out. All right, let me draw the allylic radical. Here's your allyl group here. Here is your single dot right here. Okay, and here's the thing about what sometimes makes this radical stuff so not confusing, but time-consuming and tedious. I'll admit tedious. You just can't use one arrow and be done with it. You can't do like a one and done. You have to account, if you're moving one electron at a time, you're moving one electron at a time. That means all electrons will move singly. All right? So this guy here is going to form another, it will form a double bond right there, and you'll form the allylic radical right there, right? Okay, so there's that. So half arrow, there's that there. All right, and what I do, and you have the choice of doing whatever you like to do here, and I'll show you what I do sometimes for some space issues, but you can do whichever you want, and I'll show you a few different options. So I'm moving one electron here from there to there. All right, and recall, I still have, you know, two hydrogens here, right? All right, so now I want to move one electron at a time from this pi bond. Right, so I can either go from here and do a half arrow here if I want to, but sometimes I get, this is a little bit too crowded for me. So I just go from the other side. I start halfway in here roughly. I go zoop, right? So you can sort of track where one half of the electrons here, one half of the pair is swinging down from here to there, and from there to there, forming another double bond. Then you have one more electron to account for. Now again, you're not seeing any electrons here on purpose because it's a line, it's a double bond, right? So you just draw another from the same origin essentially. Start there, draw to the end of that carbon like that. Okay, so now what do you have? Well, you still have a resonance, you still have the carbon backbone. You would now have your new double bond that you just made, and now you have your radical right here. All right, so those are your two canonical forms of that. All right, and that's what it looks like. That's what the resonance form of this allylic radical looks like. Okay, and to go backwards, you just do the exact same thing here, but backwards. All right. So let's just compare this to the allylic cation and anion again. Let's do this again. All right. So here's your cation. Ooh, that's a little bit sloppy. All right. There's your cation here. From the electron density to where you want to go, we're using your convenient now, right? Double-headed arrow, double barbed arrow, resonance arrow. And there's that, and there's that, and that's good for your carbocation, right? Now for your carbanion, all right? Anion, okay? Draw the same allylic species here. What a weird angle I'm drawing at. Move this microphone. All right, how's that? I really need a gaffer or a best boy or a grip. One of those things that you have in movies, I think. I definitely need a personal assistant. Okay, so here's the anion, and I will draw my pair of electrons right here. Right? There's your pair of electrons right there. Here's your negative charge right there. All right. And then, so to draw this now, I'm drawing from my electron density to where I want it to go. So I can either draw it from my pair or the charge here. But I'll just draw it from the pair. Right, from there to where it's going. Then this will swing on out. Okay. Again, we've sort of summarized this before, right? We've seen this before in when we were learning about the allylic systems. Okay. All right, and there's your boop boop. Ooh, he looks mad, doesn't he? Ugh. All right. Don't scowl. Don't scowl at me, electron pair. All right. So so there's that. So here is the carbocation, the carbanion, and then here's your allylic radical. Here's how they all compare. Look at just take a gander and just sort of compare them out. Now, here's what I recommend. Obviously, don't just take my slurred scribbles here as a covenant here. Just please redo this for yourself and make sure this makes sense to you, and make sure this carbocation motion and this carbanion motion is very, very, very natural to you. Okay, that's what you definitely want to be able to do. All right, let's draw one more. Let's draw the benzylic radical. Okay, the benzylic radical. Okay, here's something that's a little bit more involved, and I won't draw all of them because it gets, again, very tedious, right? And I don't know when I'll start singing, and that I have to cut this up before I start singing, because that's, you don't want to have that. You want to be able to enjoy your life. All right, I'll draw that. How straight? See? Oh, okay. All right. So here's your toluene system, but this is a benzylic position. Here is your benzylic radical right there. All right. Now let's draw a few canonical forms of the benzylic radical system. Okay, so again, tedious as all hell, but let's just take it electron by electron. All right. I'll try and squeeze it in here, although it's going to be messy. So half arrow there, half arrow there, and you always have to. And is this a principle? I have to figure this out. Yeah, I think what you can do here is that for every radical motion you have to move at least three half arrows. I think that's sort of a principle. I have to figure that out. I have to make sure that that's general before I really tell it to you. But it seems to me like every time I do a radical thing, a radical push, I have to move at least three arrows. All right, so there and then there, right? Because this forms a double bond, and then this is where you park your electron, your single electron. Okay, here's your resonance. Let's draw your ring here. All right. This works, of course. It's totally legal. It's not wonderful because you are breaking aromaticity and breaking resonance. That's not something you really want to get into for stability, but if it's part of an argument, it's part of an argument. I mean, it is important. All right. Now we're into the ring. We've now jumped from the diving board into the cool ocean of benzene radicals. Now let us just go from there. Again, half arrow there. You can do half arrow there, or you can come from underneath and do half arrow. It's up to you, whichever way you want to use. Okay. Now we're not done there, right? You got to do one more electron push, and park it right there. All right. And there's your radical right there. All right. Oh hell, we'll do one more. All right. So there, then you can park this one right there. All right. And this is essentially the complete picture of the benzylic radical system. Okay. Zoop, here and here. Just like before, notice a cute little pattern here. Look at this. This is a benzene. This is a benzyl radical, sure, but look at it. What really is it? It's really an allylic radical, just like a benzylic carbocation is really an allylic carbocation that's really souped up. So a benzylic carbocation is really an allylic carbocation. The same way this is a benzylic radical, but it's really just a bunch of allylic radicals. See that? These are all allylic resonances, really. Every one of these pushes are allylic resonances, right? That's why they're so wonderfully stable, all right? So that's why that is. So, all right, so that's something to know, okay? That's why it's so stable. All right. Vinylic free radicals are especially reactive, and these are pretty crazy, okay? So, we just switched, by the way, units here for some reason. That's how, I don't know why, but that's how this asset came to me. It's not wonderful, but let's compare it as is. All right, so the vinylic free radicals are especially reactive. This is your vinylic radical, okay? Because there is no resonance stabilization, just like vinylic cations and vinylic anions. There's no stability there, okay? So that's something you should definitely know. And it's really hard to form a vinylic radical, okay? And so we won't really be doing a lot of that, in this semester at all, or even next semester. It would be more for graduate if you really are interested in it. Okay, so yeah, so there's that. All right, so yeah, this is pretty high. We will care more about how to care more about our alkyl radicals here, and our allylic radicals, and our benzylic radicals, especially allylics. Allylics are very, very, very fun to work with, okay? And and I don't like to do a lot of pre-summary. It just seems a little bit like knuckle cracking, and I'm cracking my knuckles, actually. Look at that. I'm physically doing that, all right? It's just a lot of knuckle cracking. It's a lot of throat clearing, but it's worth talking about. There really are 6 key arrow pushing patterns for radicals. And I like, and normally I don't like this, but I like how Dave did this one. All right. So what do we mean by like patterns here? Whenever you do a radical electron push, it's going to fall into one of these categories roughly, right? There'll be homolytic cleavage where you break a bond in between, right? You'll have an addition to a pi bond where a radical will attack a pi bond, right? And then attach to it, right? To make a new bond between those electrons, which is right there, right? You have a hydrogen abstraction here, which radicals can also do. A halogen extraction, which is very, very, very popular to do. An elimination, which you don't see a whole lot of at this level, but there will be that. And of course, a ton of coupling. Okay, and if you really look at it, he didn't do this, but I think that it would really be good to look at this in terms of what these really are. These are initiation steps, these are propagation steps, and these are termination steps. And I'll show you what these things are in the next few slides. This is the next thing. This is, by the way, the most, to say this is the most different thing you've ever learned is really a weird thing to say, because you're only can be different, not very different, right? It's just difference is only an off or an on, all right? But we're going to use radical chemistry and our knowledge of radicals, right, to be able to to affect different chemistries. And this is going to be a real great use of radicals for you, because this is the first time you'll ever be able to radically initiate an alkane to be able to add a chlorine or bromine or whatever, or some sort of a moiety that can be reacted with a radical directly to the alkyl chain. All right, let me show you what I mean. It's a very powerful thing. All right, so let's use our electron pushing skills to change methane into methyl chloride. Okay, and here is what I would consider like the stereotypical treatment of this thing here. It's a very weird way to look at a reaction mechanism, but it's what we do for radicals. We do this for radicals because radical chemistry is very messy, and we need to categorize each of the steps in a radical mechanism. All right. Whenever I ask you for a radical mechanism, I'm going to want something like what I'm about to show you. If I just want what happens, after a radical mechanism, and just want the product, then just give me the product or the reagents or whatever. But don't worry about giving me the entire mechanism. Only when I ask you for the mechanism, that's when you have to give it to me. All right. And I say this because this mechanism is sort of long. All right, but it's easily understood. Okay, so let's just do this. All right, so methane plus Cl2 and H nu, right? H nu, this is a photon. It's a packet of energy, right? We'll give you methyl chloride and hydrochloric acid. Let's go over how we make this. All right, and let me show you the significance of why this is so wonderful for you. Up until this point, you have never done any chemistry on an alkane, right? That's why it's so sort of wonderful for you at this point. I'm going to highlight one hydrogen here. No, I'm not going to start. I'm going to start somewhere else. I'm going to start here. I'm going to start at this guy here, all right? I'm going to start at the initiation. Initiation. I can't. This stupid pad. Initiation. All right, this initiation means exactly what it says. It's going to initiate the radical process. That means Cl. Here is your purely covalent bond here. You treat this guy here with some photons, right? And what you have here is the initial radical cleavage. So if this guy here breaks, then you generate 2 moles of Cl dot. All right, that's the end of the initiation phase. All right. All right, so now we're going to move on to the propagation phase. The propagation phase. All right, the propagation phase is you have some radicals and you're going to make some radicals. All right, propagation. All right, take one of your radicals on here, chlorine dot, and you treat it with a mole of methane. All right, I'm going to highlight a single hydrogen from that methane. All right, there's that. I'm going to put the radical, I'm going to point it to somewhere in between the radical and the hydrogen. And then I'm going to pull this hydrogen electron pair here, from here to here, because I'm making a new bond right there. All right? And because everything here moves essentially in threes for this kind of chemistry, this guy here has to move on out like so. Okay. So what did we just form? We just formed HCl. Hey, we formed HCl plus CH3 dot. Okay? From here, right? CH3 dot. Okay? Propagation. You start with some radicals and you end off with some radicals. All right? So there's that. All right? But we're not done. We're not done. All right? You take the CH3 dot here. H3C dot. You treat this with another mole of chlorine. Another mole of chlorine. Radical there. Radical there. Radical there. You start off with some radicals, you end off with some radicals, all right? You're making some, so now you'll make some of your all right, plus more Cl dot. This guy here comes from this guy here, and I'll just put this one here, and I'll say I'll use a line on top. This guy here comes from this guy there, right? See that? But it's important. Propagation. Start with some start with some radicals, end with some radicals. Start with some radicals, end with some radicals. Termination step. This is the easy step. Termination means you just terminate this entire reaction. Termination. I'll just say termination. Terminated. Terminator. That's my. I'm sorry. That's not my. That's my bad Arnold. Yeah. That's my Arnold. How's that? Eh? That's weird enough. Terminate. Oh man. Termination. All right, there it is. Woohoo! All right. This just means take every available radical and combine it with itself and everything else. Sounds like a lot. It's really not that bad. Let's start off with chlorine. Take the two chlorines and then go in reverse. Cl dot Cl dot. Half arrow. Half arrow. Right? All right, and Cl. All right. Where else? So we've done the chlorines. All right, let's take this guy. All right. H3C dot plus a chlorine dot. Cl dot. Right, there's that. So then you make H3C Cl, which is this guy up here, this guy over here, and of course this is our thing that we crave, right? All right, and we have one more to make. Yeah, one more weird thing to make, right? So we've combined the two chlorines, we've combined the chlorine and the methyl radical. Now what's left to combine? Well, I guess two of these guys. Two methyl radicals. But that's not part of our thing. Why would we combine two methyl radicals? Because it's there, right? We generate a radical, it has to be accommodated. It has to be accounted for. All right? So take CH3 dot. I'll just draw another dot here. Dot CH3 dot right there. All right? And then you end up making ethane. So ethane here is a byproduct of methyl chloride production in this process. You don't see it because sometimes you don't draw all the all the side products. But rest assured, this is definitely made as a byproduct. But I want to show you something that's very important here. Okay, look at this. Again, I'll switch pen colors. Boop. Look at me with that with the technology. Red. No. Oh. Oh hell, I'll use green because we're a green campus, right? Green chemistry. Ooh, green chemistry. All right. Initiation. You're making some radicals. You're making some radicals right there, right? Right? From no radicals to radicals, you're initiating the radical process. In propagation, you're beginning with radicals, you're ending with radicals. You're beginning with radicals, you're ending with radicals. It's important to see this symmetry in this pattern here, okay? Now look at this. Look at termination. It's initiation in reverse. You just have radical, 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 radical. No radicals on this side. So initiation, radicals on the right. Propagation, radicals on both sides. Termination, radicals only on the left. All right. So that make sure that you understand what these words mean and how they directly give you hints to what you should do. All right. Little caveat here. This is not how chemistry works. You don't just put methane into a flask with Cl2 and H nu and be like, okay, do your chemistry. I'm gonna go and have lunch, right? And then come back and it's like, all right, I'm going to do the initiation step, now the propagation step, and now the termination step. The flask does not see, nor does it care about any of this. This is our little human way to understand how radical chemistry works. But trust me, when you bubble in methane into some solution and then you hit it with Cl2 and some light, everything happens here. The whole mess happens. Right? This is just our way to make sense of it. All right? There is nothing in the flask that says, now I'm the propagation step, I'm the initiation step, now I'm the propagation, and you're going to be terminated. He's dead tired. And I'm sorry. I keep on doing the Arnold for some. I'm sorry. All right. So anyway, so there's nothing in it that says I'm termination, I'm propagation, I'm initiation. No, this is just our way of figuring out the categories of the reactions at this point, okay? So there's nothing crazy about it. It's just how we determine how things look, okay? And how to put them into categories, all right? All right. Practice this. I promise you it will be on the final exam. I promise, okay? This is a very important reaction. It's a very important standard thing to know for undergraduate organic part 1, definitely, all right? There we go. And it's gone. All right. So what does this slide? What does this whole slide say right here? This slide here just has a lot of very simple things here. It says that it's very hard to stop a radical reaction, right? It's very difficult to stop one or to control it. So you just can't say like, oh, here's methane, here's Cl2, and I want 1 mole of methyl chloride, and then that's it. No, there's no way that it'll stop here, right? It'll go from here and it'll go all the way to the very end, to stop a carbon tetrachloride. So it's very difficult to stop it. You can stop it in some ways, but it's going to be sort of a mess. All right. So it is very difficult to prevent. Okay. Especially when you have an excess of chlorine in there. Why is that? Because if you have chlorine in there, then it's just going to overreact, and if there's more moles of Cl2 in there, it's just going to keep on pulling off those protons, keeping on reforming Cl2, and then that methyl radical or whatever alkyl radical will keep on attacking that Cl2. It's just a stoichiometry thing. Once you start a radical mechanism, it's hard to stop it because of a chain reaction. These are things that you'll hear about in movies and in the news. But once you start chain reaction, that just means you just need to get something started and it goes by itself. That's why they're so scary. In industry, these could be fatal. So you want to really control your. I always joke around about organic chemists being control freaks. One of the reasons why we want to be control freaks is because we want to sort of live a little bit longer than average. So we have to control about control the thermodynamics of a reaction and stoichiometry because we don't want something to be runaway, right? A runaway reaction is also a reaction that is undergoing an uncontrolled chain reaction, all right? And so once you start radical stuff, it's hard / impossible to stop, okay? So this is just what this is, all right? So that's all that I'm just trying to say there, all right? Nothing too crazy. Draw a reasonable mechanism that shows how each of the products might form in the following reaction. All right, well, this should be easy to figure out, right? Cl2 and heat just used the same mechanism that we talked about a few slides ago, right? But how about this dichlorination process? How about this chlorination process? You know, how would that form? How would this form here? And we won't go through the whole slide again like we just did a few minutes ago, but you might imagine that this might come up from the reaction of, for example, this might come up from, I'm still in green. I want to go back to blue. All right, you might have, there's that, and you might have that radical right there, plus plus another Cl dot radical, right, in your termination step, or one of them, right, in one of your steps, either in your propagation or your termination step, because you generate product in both of them, right, as you noticed, right? So that's where that might show up. That's where that might show up. But you say, well, how does this show up? Like, why would this happen again? And that's what I just tried to say in this prior slide. Like, why wouldn't it happen? Why couldn't you have this just go right back up to the initiation step, have another Cl dot come over, rip off a primary proton, having and have a primary radical, and then have this primary radical react with another chlorine dot? You can do it. It can happen, right? So I mean, that's if it can't happen, it will. Just like we talked about in that prior slide. We chose methyl, right? We chose this one. We chose methane. I'm sorry. We chose methane because there's only one type of proton on it. There's only that one here. But if you have a molecule that has multiple types of protons on it, like you have primaries and secondaries, then there's no reason why you couldn't have, why you couldn't have reactivity both here and here. And there's a big principle that sort of dictates all of that business. All right, so that's why we have to be very careful. How that what to look at and how to think about it. Okay, so yeah, go back and see if you can generate this guy here. Do out the chemistry and get this guy. Right, very easy to do. Then resubmit this guy to the same reaction chemistry. Take it back up to the initiation step, and then simply pull one of those protons, those hydrogens, not protons, one of those hydrogens, and then that's how you get to that. Then that can react with another mole of that, right? Or another mole of Cl-Cl, right? Whichever way you want to do it. Either you can react it in the propagation step or in the termination step, whichever way you'd like to do, whichever way floats your boat if you're seafaring. All right, that's how that would form. So that's to get that guy. That's how that would form. And then to form this guy here is this is as simple as this forming. Instead of pulling off the middle proton here, you'd be pulling off the primary proton right there. That's all. Now, how does this happen? How could that possibly happen? Well, and where does that happen? More specifically, where does that happen? Let me clear the deck a little bit. Where does that happen? Well, this sort of looks. Look at this. This sort of looks. Look, you have 1, 2, 3, 4, right? So you have this guy here. This sort of looks like this, right? Wow. Then what the hell's that? Oh, that could be easy though, right? Look at this. Well, remember in your termination step, you have to combine things. You have to combine every possible radical. Imagine if there was a radical that looked like this. And imagine if there was a radical that looked like that. Right? Look at that. That will give you the exact thing that this is. Right? There and there. All right? So that's how you form that. All right? And this is going to be formed in the termination step. All right? Am I really doing this again? Terminate, radical. Okay, there you go. Terminator. Sorry. Terminator. All right? So there's that. And so that's how this is formed. Okay, so again, so your question might be, so, all right, I dig how this forms, right? That's fine because we did it here, but how does this form again with the primary radical? Well, you got to go through the primary radical to make this guy. That's how it forms. And then you might say, again, why are these even seeing each other? These are two different processes. That's exactly the point. The point here is that in a radical process, it's hard to control things that could have multiple products. That's why chlorination and bromination are good, robust chemistries, but they're not very. In terms of selectivity, you could do a little bit better. All right, so I would never, ever, ever give you a question where I'd have you do all of these, initiation, propagation, and termination steps, and do everything, and then combine something or other. But I would ask you something very much like this, because you should be able to know that multiple products can occur, right? And then you should be able to rationalize where a weird side product might come from, just based on what you know from your starting material. All right, so definitely practice this and make sure you can get to each one of those intermediates, and really give it the old college try. Don't just get very frustrated and then be like, the hell with it. No, just go there and be Arnold, and be a Terminator. I mean, don't impregnate your maid or anything, or your nanny or whatever he did. But wow, it's turning into like a real TMZ episode, isn't it? All right, so. Just be tough about it, and don't back away from this. This is your last hump before the end of the semester. There's this, and of course there's the ever-present synthesis. But this is the last major new thing you'll be learning. Okay. All right, and so we use for plain old table grade garden variety halogenations. We use we use chlorinations and HNO. We use photons essentially, right? But sometimes doing this chemistry here using just chlorination, 58 kcals per mole, it might not seem like a whole lot, but it's a pretty high enthalpic value, and we might not want to sort of boil our reaction to get to or really heat the hell out of our reaction to get to this level, right? Because what'll happen is that we will form the chlorine radical, but if we have any other, anything else in the molecule that has weak bonds, we might break those bonds because of this heat. So what do? Sometimes we use radical initiators. All right, and believe it or not, you've already been using them, and you might not even know it. All right. And this guy right here is without the initiator. Here's just a plain old chlorine plus heat or HNO. By the way, we can use heat or light for this, whichever one we want to use. But the enthalpic value is the same. But let's say we want to use a different initiator, right? We could use a few different ones. One of them we have is that this could break in a peroxy bond here, which is 20 kcals per mole lower than that, right? And then that's good, and that's a nice gentle way to form a radical initiator, which is sort of good. Or we can use maybe like an acyl peroxide, right? An acyl peroxide. What's an acyl peroxide? Well, you know what a peroxide is. A peroxide is any alkyl oxygen alkyl bond. That's or here's hydrogen peroxide. Right? Here's hydrogen peroxide. We've used butyl peroxide before. Right? And acyl peroxide just refers to this species right here. This carboxylate is also known as an acyl group, right? Sort of weird. I'll talk to you more about it later, but just remember this is an acyl peroxide. This is an acyl group roughly, even though it's also a carboxylate. It's interchangeable, but specifically look at this enthalpic value. It's even roughly 10 kcals lower than your peroxy radical. And why is it even lower? All right. So which initiator above initiates reaction most readily? Of course, is the acyl peroxide, because it gives you because it's the lowest overall enthalpic value. But why is it the lowest? Why is it the most easily broken or the most easily cleaved? Why is that? What you might imagine is that you have some beautiful radical resonance here, right? You can park your radical right there in the oxygen, but we all know it's not going to stay there. Nope, it's going to do one of those, and one of these, and some of that, right, to give you, right, some of this. All right, let me just see if I can radical double bond right there. Okay, boop, 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 boop. All right, and there's that, and that's the reason why this is the lowest enthalpic value, because you have resonance stability associated with that radical as well. So you can, and just like we showed with the allylic radical, you can definitely have resonance stabilization. All right, so that's the initiators, and you've already used this before. How, you might say? What are you talking about? Okay, all right, stop yelling at me. Wow, stop screaming. You guys are so mad all the time. All right, look, HBr, and toot. HBr on peroxides, your old friend, the anti-Markovnikov addition of HBr across double bond. You've already been using that. This is the radical mechanism I've been talking to you about. Okay, your book will tell you, oh, it's HBr and roar, which you should never use because that's terrible, and that would make you a bad person who is always sad. All right, crying, and drooling. All right, so you never want to use HBr and roar. HBr and, let's just say, tributyl peroxide. This is a radical initiated process. So that's how that's the thing that I said, don't worry about until we learn radicals. Well, here's the radicals. All right, here's the radicals. All right. So there's a lot of things, and we'll go into that mechanism in a little bit. Okay. All right. So here's something. Okay. We need to talk about, radicals are, for our cases, good for the most part. They are things that are helpful to us in terms of our chemistry and our chemical transformations, but they're overall sometimes can be bad, right? And so, we have things here that we want to use sometimes called initiators inhibitors, and these inhibitors will sort of scavenge some electron density, right? From like oxygen diradicals or from other radicals, all right. And for example, here, if we have this oxygen diradical here, that this is just one form of oxygen that would be sort of pretty bad for us, okay. And so this is the thing that we need to be able to inhibit sometimes, because if we don't inhibit oxygen, then it could really sort of tear apart some other of our molecules, okay. And so how can we, what molecules can we use to inhibit a radical process or to stop a radical process? All right. Well, one of the things that we can do is, like, we can use hydroquinone as a radical inhibitor. All right. And how does that work? All right. How does that work? If we have some radical that we want to be able to inhibit and stop, we can just throw in hydroquinone. And this guy here will just grab, right, one of those protons right there and give us this resonance stabilized radical hydroquinone. All right. And this R group here, which is our radical that we want to inhibit, is sort of like left to be sort of a neutral, non-reactive moiety, which is a good thing. But because this has 2 moles of OH there, this guy here can absorb 2 moles of this, all right, which is good. All right, again, there's that, and then there's that. Again, giving you another radical right there. But if you have this diradical right there, you have the ability to be able to push these 2 radicals into the ring to make the very semi-safe and pretty non-reactive benzoquinone chemistry. All right, it's pretty non-reactive, and it's pretty easy to get rid of if you want to purify your reaction. Okay, and so you can use hydroquinone to form benzoquinone if you want to inhibit a radical process, because it will just absorb radicals, right, and make them into very very neutral species, okay. And so that's one way of sort of dealing with radicals. All right. So okay, in terms of thermodynamics for radicals, it's pretty straightforward stuff. We won't go into it that much, but I'll give you sort of like the 101 on it. So in a radical halogenic process, we want to have a very enthalpic process here. Okay, so we want to have this where you have a reaction given a minus sign right here, because if you have a minus sign for this, you have a negative enthalpy, which means it gives off some energy. So that's something that we really sort of want to have, and that will make a exothermic process. Okay, and so how do we do that? Okay, so because T delta S we really don't care about. We don't care necessarily about the entropy of the reaction, because semi close to zero in a very closed process here. We will just say that this is essentially close to zero, so we can simplify the equation to delta G is roughly equal to delta H to enthalpy. Okay, so Gibbs free energy is roughly equal to delta H. Okay, so considering the bonds that break and form in the reaction, estimate the delta H of halogenition for each of the halogens in the table below. All right. So how do we do this? Or how do we do this? We simply list off underneath each one of these compounds here what they are, right? And then underneath the compounds that are the products of the reactions, we list these as negative negative enthalpies here. So let me see if we have. Let me see here. So since this guy here is going to be methane all the time, this will be 435. 435 plus 159 if we're talking about fluorine here, and then we're going to say plus a negative 456 plus a negative 569. And if you add up all those numbers, you will get an extremely negative enthalpy of reaction. Okay, which is something that you might expect from fluorine. All right, and so there you are right there. All right, and so this is sort of a generic sort of table as to what I'm talking about here. Just take the positive values of enthalpy for the starting materials and a negative value for each of the products, and then if you add up all of those numbers, right, they'll come out to values of the appropriate enthalpies of reaction. All right, and notice if the reason why we never use fluorination or iodination is because fluorine is way too reactive, right? It's way too reactive. It's sort of like your tea Richard Madden after a few too many. All right, so it's way too reactive, right? It's overreactive, one would say. All right, so there's this guy here, and it's just because it's way too much heat of formation right here. Now, similarly, but on the other end of that spectrum, look at iodine. Is plus 55. We actually have an endothermic or an endergonic reaction here, right? This is a plus 55 kgs per mole, which means that this reaction here is really not spontaneous. So it's not going to happen for us. So that's something to consider. So this is overreactive. Ooh, boom, right? This guy here is like, whatevs. All right? So this is overreactive, this is underreactive. That's why we're always in the sweet spot of bromine and chlorine, because they sort of give us roughly this, nice stable sort of reactivity for this stuff. Okay. Here's something to know sort of qualitatively. I'm not going to ask you any of these values, of course, right? So for chlorination, both steps are exothermic. So a little bit of heat, a little bit of light right here, boom. And it goes, right? It's pretty much spontaneous. Once you hit it with a little bit of light, it's gone, right? It's ready to go, right? But for bromination, the first step here, you need a lot of energy to get it going, right? And then the second step here, once you get this going, then you're fine with it, all right? So once you get over this hump, and then the rest of it sort of just goes by itself. But this first step here is going to be endothermic. So you have to sort of get over that, sort of get over this this hump, okay? And that's something that we sort of have to deal with. All right. So what does this mean for us? All right. And let's just look at this sort of boring slide, okay? Hammond's postulate. All right. Hammond's postulate. So Hammond's postulate means that if our reactants are closer to the transition so if our reactants are very high up to the transition state, our transition state structures will look like our reactants. if our transition states are closer to our products, our transition state will look like our products. It sounds sort of obvious, and it sort of is, but it means a lot. This is sort of a postulate that he sort of figured out, right? And so, does this make sense to us in any sort of a way? It does, right? Because here, our reactants are already beginning way up here at this level of energy, right? You need a very little activation energy to get this guy going, unlike this guy here, where you need all this activation energy to get it going. All right, you just need a little bit to get it going, and then hits the transition state. So it almost makes sense that the transition state looks like the starting material, because they're just so close together in terms of their energies, right? And so this just needs a little bit of a push, a little bit of heat, a little bit of light, and then it's going to go. All right. Right, this guy here needs a lot more energy to get it going first, and then once it goes very, very, very fast at the very end. It's endothermic, but it's still gonna be fast from the transition state to this intermediate. All right, but you have to get over this big hump first. Okay, chlorine requires more energy than bromine to form its radical. Right, 243 versus 193. So it has more. So it's more energetic, and/or can abstract a proton faster. Right, then and so this will pull off this proton faster, and it will attack the most easily available proton on the molecule. All right, and so I'll tell you this here, but then I'll just show you in your other slides. It'll be a lot easier to see, sort of practically speaking. Let me just give you the analogy here. Okay, so chlorine is hungrier for any and all protons than bromine is, in terms of the propagation step, that pulls off that first proton. So chlorine will be like, I'll take any proton that's close to me. Bromine's like, I'm cool, I can deal with the best proton, right? And the way I look at it is that, like, Jesus, I don't even know how to. I used to use hamburgers for this, and I always say or like a steak or whatever. Like, how do I do it? Maybe burritos? Crap, give me a good food analogy. I don't know. Oh no. All right. I'm a Chipotle fan, not an Anna's Taqueria fan. All right. I know. Sue me. I love Chipotle. I can't deny I don't. Okay. So I love Chipotle. All right. But let's say I'm chlorine. And I really need a fajita burrito. I need a chicken fajita burrito with the salsa verde on it. I really do. I just need it. All right. And Chipotle is in so I live in Hudson, New Hampshire. So Chipotle is in Nashua, but there's an Anna's Taqueria right down in Wyndham, which is very close to me. So I'm like, the hell with it. I'm hungry. I'm gonna go to Anna's Taqueria and shove a burrito in my face and be happy with that, because at least I'm getting something to eat, because I'm starving, because I'm chlorine. All right. So chlorine is hungrier for even the cheap ass burritos that are substandard, as far as I'm concerned. I'm not paid by Chipotle. I wish I was. All right. So there's that. But if I'm bromine, I'm closer to the Chris Katz variation of this, right? I'm bromine and I'm hungry, but I'm not that hungry, but I can wait for Chipotle because they have a superior product. Okay? And the tattooed pretty people behind the counter flirt with me, possibly. Maybe that's why I like Chipotle so much. All right? So I'm bromine. I'm cool. I'm hungry, but I'm not that hungry, so I can afford to drive down to Nashua and grab some cool Chipotle, the chicken fajita burrito with their awesome lime chips. All right? I really, right now, want a goddamn burrito. I do it to myself all the time. I'm an emotional eater. You should know this. I think you know it by now. All right. So that's what it is. So chlorine is hungrier for the closest burrito than bromine is. All right, so chlorine wants any available hydrogen it can get, no matter where it is. Bromine's going to be more selective for a certain type of hydrogen. Okay, that's important to know. Okay, because here's something that's really, really useful for you. It might not be obvious in this slide, but it will be in the next few slides. All right. So let's just say this. Okay, let's just say we have propane here, right? Propane here, and we hit it with light and some chlorine or some bromine, and then there you go. Okay. For chlorination, 60% of it will give us the 2-chloro product. 40% of it will give us the 1-chloro product. So roughly a 1-to-1 mixture. Not 1-to-1, this is 60-40, but it's close to 1-to-1. So in this case, I would say this is not very selective for secondary over primary. I would not say that. All right? But for bromination, look at this. 97% in the secondary position versus 3% in the primary. Holy mackerel, right? This is way more selective. So what do you think I'm choosing if I want to alkylate or brominate a secondary position? What will I reach for if I want to halogenate a secondary position? I'm going to reach for my bromine, for my Br2, not my chlorine. My chlorine is not selective enough. 60-40, roughly 1-to-1, versus 97-3. Come on, right? So why is that in this case? In this case here, well, it might be a little bit of statistics. It could be like, well, there's 6 primary hydrogens to two secondaries, and that's why, like, it's, this might be thrown off a bit. That's why it's like there's more chance that it's going to the primary versus the secondary, because there's more chances to go to the primary. But the fact remains that this is still not as selective as this guy is here. Even with those statistics, this is still going to go 97% to 3. So 97-3 versus 60-40. All right. So if you look at the free energy diagram, right? The free energy diagram with hydrogen abstraction for a primary radical, it's going to be a pretty high energy to pull off a primary radical, right? And it'll also give you a not so stable of a product. So not so stable, because if it was very stable, it would be a lot lower. If you pull off a secondary proton, again, easier to do, because overall it's going to be the more stable product. The lower the level down here, the more stable a product it is. So that's why, right? And so it's a lot better if something just pulls off a secondary. If something pulls off a secondary proton, you end up getting a more stable product anyway. Right? Because if it's secondary radical and the level energy is down here, very low energy, so it's very stable. That means that when the reacts with a radical, it's going to still continue to be a very stable product. So it's interesting to give you a secondary. But the fact that chlorine here still has a lot still has a lot of energy to go for that primary, means it is less selective. So here is a very good principle called the selectivity reactivity principle. Chlorine is more reactive and less selective. Bromine is less reactive and more selective. This principle is not just a principle in chemistry, but in appetite, both for food and for love. You're hungry for love, so maybe you might be a little bit less selective in your immediate source of love, just to fulfill some needs. Versus you're like, you know what, I'm cool with love. I'm gonna wait for Mr. or Mrs. Right. I'll be more selective. I'll be less reactive and more selective. But chlorine's like, no. I'm beer goggling and I need some lovin'. All right, so chlorine here. Why am I just trashing chlorine tonight? Jesus, it's like, what did it ever do to me? It never took a girlfriend of mine. I don't even know idea what my problem is. I have no idea I don't know what's going on. All right, so chlorine here is way more reactive, and way less selective, right? Way less selective. Bromine here is way less. So this is way more reactive and less selective. This is way less reactive and more selective. Look at that. It's beautiful. This is a really great thing. It's a really great thing for you, because let me show you this next thing that's coming up. All right, important thing here. Let me just get the page number. What page is this? What page do I have to be on here for this? Stupid. Okay, yeah. Page 508. So there's a mistake in your textbook. Okay, correct it. Okay, the mistake. So change your numbers. So Dave wrote that, let me get a stupid book here. Okay, so Dave wrote that this is 7228. All right, and the real numbers should be 3565. I called him out on. I called him on it actually, and I said, "Hey, you know what this is happening in your textbook?" He's like, "In the year and a half this book has been out, no one's caught that mistake." So you can thank your old Dr. Katz for that one, right? Of course, it has to come to one of the more annoying people like me, right? But anyway, but please change the 7228 to 3565. All right, these are the real values. That's still cool. All right, so okay, so fix that in your textbook. And I don't even think that's in your errata. It might be, it might not be. But anyway, I know it's fixed in the second edition, I hope. Okay? So, all right. So there's that. Okay. Look at this. Look at this. If you take 2-methylpropane and you treat it with HNu and chlorine, you get 3565 chlorination at the primary position here. This is the primary position versus the tertiary. Right? Look at that. Pretty cool, right? Look at this. HBr and HNu. Look at this. 100% ultimately, like 98% roughly, of the tertiary versus none at the primary. None at the primary, all right? How awesome and productive is that? Pretty damn productive, all right? On both counts, right? You could say, you could say in a synthesis to me, if you'd like, if you want to build a molecule, you could say that, okay, I want to brominate something at a very specific position, and I will use bromination to give me the most internal bromination possible, all right? So you can do that. You can totally do that, all right? And just say, all right, fine, if I want to brominate there, I'll hit it with HNu and Br, or so HNu or light and Br2, and I will be assured that it will go there. But let's say you want to alkylate, or you want to chlorinate there, or there. You know what? It's not the best thing, but you could say the major product will be chlorination here. So if you want to halogenate there, use chlorine. If you want to halogenate here, use bromine. Not just for this, but for anything else that you might imagine, that might be helpful for you. You have that guy, you want to brominate, that bromine's going to go right there, right? If you want to halogenate, chances are your halogenation will go right there, and right there. But I gotta tell you right now, as you guys get better and more adept at synthesis, you guys will get to be sort of snobbish about this, and you'll find a way to work bromine into everything, because you know where bromine will go, and then you can work with bromine wherever. You can brominate, then you can do an elimination, then you can do something else, and then something else there. So you can really work with bromine for many of your cases, all right? So you might not even need chlorination anymore, all right? But bromine is very helpful, and so is chlorine. But I think you can't deny the utility of bromine going to the most substituted carbon. I mean, that's a general principle, and it's extremely useful. All right. So let's continue to beat a dead horse. Which process is the least regioselective? Well, primary is all a wash because they're all ones. Let's look at secondary versus tertiary. Look at so bromine's the most selective at 16 to 82, tertiary to secondary. Look at chlorine, like essentially 5 to 4, tertiary to secondary, and essentially 1 to 1 with fluorination. That means which is the least regioselective? Bing, 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 bing. Our friend fluorine. All right. So that's it. Okay, and we just talked about the selectivity principle. All right. All right. So let's talk about these little, very simple, simple compounds right here. Okay. So for the reaction below, draw the structure for every possible mono-bromo product. Monobromination. Okay, make sure that just means like it'll be multiple products. All right, but they'll only have one bromine on them. Of course there are products with multiple bromines on them, but we only care about the ones that have the monobromos. Okay. All right. You know what? I will just do a single one here, and I'll just point to where they should show up, just to save time and save space, and have you not be able to decipher every scrawl that I have here. Okay, so monobromo. So here is one position that might be monobromine. So the bromine could be there or there because these are equivalent, right? The gem dimethyl, the geminal dimethyl positions right there or there. You can't have a bromine right here, right? Because you better not put a bromine right there. Why? Because this carbon here has 4 things on it, and if you guys give me a Texas carbon, I swear to God, I swear to God, oh, you don't even want to know. All right, so right there and right there. All right, no Texas carbons. All right, so that's one monobromo product. There's another monobromo that could be right there. There's another monobromo that could be right there. Another monobromo right there, and another monobromo right there. I just chose every proton that was different. That's why I only chose one of those, because this and this are equivalent. That proton, that proton, that proton, those protons, those protons, those, and those. So you have the possibility for 5, count them 5, monobromo products. Okay? Which one will be the most major? The most major. Which one will be the major? Which one will be the major? I don't know. My guess would be the major is easy to figure out. This guy here is going to be the major one, right? Mage. Yeah, that's my guess. Which one will be like the second most major? This one. Why? Major's the tertiary. The next major would be the secondary, and then tied for minors would be here, here, and here. Which ones? I don't know. If I had to take a wild stab at it, I'd probably say that if I had to rank them, I'd probably say this is the first, this is the second, I'm going to guess that this is going to be, this might be the third. I guess this might be the third, because it has carbon here with 2 hydrogens on it. All right. Then this guy here will be the 4th, and this guy here might be the 5th. That's my guess. How am I choosing those? Based on hyperconjugation potential, right? This is easy to know. This is easy to know because tertiary, secondary. There you go. Boom, done and done, right? But tertiary, all right. So not tertiary, but the third most populous one, this is a primary. So they're all primary. So they're all going to be pretty sucky. But this one here might be less sucky because it's next to a carbon with 2 hydrogens on it. This is a carbon next to a carbon with 1 hydrogen on it. And this is a carbon here with no hydrogens next to it, except for the one that's already on it. And if you remember about the hyperconjugation principle, this should be marginally more stable, right, than this, and this should be again marginally more stable than this, and this should be the least stable of all the hydrogens. Okay, so that's why I think. Okay, so there's that. All right. The halogenition of butane or more complex alkanes forms a new stereo center. All right, look at that. Chlorination, and again, this can be bromination too if you want to. Right, chlorination here. You have this guy here that you generate, but of course this is going to be, this intermediate is a radical, right? So it's going to be a sp2 hybridized carbon, right? So that's going to be something that is going to be a racemic sort of intermediate, right? So this chlorine will come from above and below the radical. Okay, so if you generate this radical, right? I'll just say it's this radical right here, right? And this radical here is in this p orbital right there, right? This chlorine here, right? This guy here, right, can be above or below the plane of this carbon right there, and it can attack from either side. That's why this is a potential stereocenter, but not a stereocenter. You will have a racemic mixture here. This will be a racemic mixture. All right. So in this compound here, you'll actually have 3 compounds. You'll have this guy here. Pardon me. You'll have this guy here, that guy there, and then that guy. So 1, 2, 3. You'll have 2 stereoisomers and another constitutional isomer. another regioisomer, right? All right. So that's something to keep in mind. This works for both chlorine and for bromine, obviously, right? All right. And just like I said before, the chlorination can come from either the halogenation can come from above or below the plane. All right, above or below the plane. All right, that's why. And they have equal probability. All right. Stop it, Dave. Okay. So the halogenation of S3 methylhexane is the most reactive on here. Why? It's the tertiary one. It is the one that is the most stabilized by hyperconjugation. And for bromination, it's going to be essentially the only game in town. All right. So this is going to be your potential stereocenter. All right. All right. And it won't be of course, you know, and this guy here will be, does have both the R and the S if you want to do both of them out like that, okay? But it's not something that's going to be that will be in any way some sort of a chiral process that will be useful for you, okay? So always assume that it's going to be a racemic mixture, okay? All right, let's do this one last thing here, and then we will call it a night, and then I will leave you to your devices, whatever your devices are. Okay. So Br2 and light on this guy here, draw the most likely monobromo products of this thing. The most likely? What do you think it's going to be? I'll wait for your answer. I'll wait forever. All right. Okay. All right. What's going to be the most likely monobromo product? I'll just say product, because I'm going to give you my best guess here. My best guess here is going to be squiggle, 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 bromine, right there, right? And the squiggle means, of course, this is either above or below the plane. We use a squiggle line to mean both the wedge and the dashed guys, right? That's what this squiggle line means, okay? Draw all possible Moss substitute products that would form in the halogenation below, including all stereoisomers. Okay? And this one here is a little bit different. It's a little bit more challenging, all right? A little more challenging there, okay? Why? We have two tertiary carbons right there, all right? All right? Here's something funny. Stereoisomers. Is this a stereocenter? Or is this a stereocenter? Right? I think that you might know the answer to that. The two likely products here that I will get, that I think are the major products, I would guess are going to be that monobromo right there, and that guy right there. Sorry, that shall be squiggle. Squiggle, 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 squiggle. All right. Why? They're both tertiary. There's that, and including all stereoisomers. So that's sort of a trick. I'm a sneak. Right? There's not going to be anything there that's going to be. I didn't generate any stereochemistry at all, right? Because no stereochemistry here to begin with. Here, it looks like it's coming out at you, but it's. These two guys here are the same. This guy here looks like a stereocenter, but these guys here are the same, right? So there's no stereochemistry there. Even when I add in a bromine, this bromine here doesn't have four different things around it. It has that's a different thing, that's a different thing, but those things are the same. All right? That's a different thing, that's a different thing, but these two guys here are the same. So this is the only thing that's really worth drawing. These are the two regioisomers that are only worth drawing, right? There's no front and back or whatever, okay? So I think that's where we will end for tonight. And I want to thank you for your time and attention, and for giving me your Friday night or whenever the hell you're listening to this spiel. And thank you for everything. And study hard, and don't get terminated. La, la.